Let's prove the following properties of distance between points, which will also be true for distance between vectors. We've been using this, and we are actually using this in illustrating distance, and we understand, such as, say, for example, the second one, symmetry, that this means that whichever point is written first in the formula, we will still get the same distance, right? So let's try to prove these properties. This may be used later on, and then very important also for structuring information. The first one is definiteness. This means that if the distance is 0, that would mean that the points indicated are just on the same position. In short, they are just of the same point, or they're equal to one another. Okay? Of course, when can we say that the distance between 2 points are 0 or is 0? That would mean we are not moving, or we do not move. Okay? So let's show that that is true. That would mean that if we have the distance between P and Q, take note that we know that the formula for that is actually the length of Q and P. Okay? Or just the same as understanding. When expanded, we know this will actually equal to whatever be the components. Let's say that P is actually P sub 1 and Q sub 1, P sub 2 rather, P sub 1 and P sub 2, and Q has components Q sub 1 and Q sub 2. Let's really show. Of course, this will become the square root of the product of the square of the difference, right? For a while, we will be getting first for Q minus P. Let's subtract them. You will have Q sub 1 minus P sub 1 and Q sub 2 minus P sub 2, right? Okay, by subtracting them. And of course, once we take Q minus P here, this is actually the square root of Q sub 1 minus P sub 1 squared, and plus the square of Q sub 2 minus P sub 2 squared. Now, if this entire value is equal to 0 as indicated here, okay, that would mean this is equal to 0. When would this expression be equal to 0? That would mean that the resulting value of these two, Q sub 1 minus P sub 1, or the square of that, must be 0, as well as Q sub 2 minus P sub 2 must be 0. Because if one of which is not 0, take note it's addition, the entire radicand will not be 0, right? So if this is 0, taking a square root of both sides, that's Q sub 1 minus P sub 1 is 0. As well as here, Q sub 2 minus P sub 2 is also 0. Which indicates, I'll be moving that later at the bottom, pardon, which further indicates that Q sub 1 is just equal to P sub 1 and Q sub 2 is equal to P sub 2. If Q sub 1 here is equal to P sub 1 and Q sub 2 is equal to P sub 2, that would mean, okay, hence, we have here, let's say, P sub 1, P sub 2 is equal to Q sub 1, Q sub 2. And what is P sub 1 and P sub 2? That's your point P, and this is your point Q. This tells us that, again, if the distance between 2 points, this further shows or proves, okay, that if the distance between 2 points is 0, then the points are just the same. Let's proceed to the second one. Let me erase this. Okay, so we're going to show that this is just equal to the other, meaning, again, whichever point is written first in our formula will have the same value. We know already that the distance between P and Q in the first example here is the absolute value of the difference of Q minus P. From here, hopefully, we can arrive to this point. Now, I would like you to put your attention here. I will be interchanging or rearranging the terms inside the notation. So you have negative P plus Q here. Okay? Factoring negative 1, you have P minus Q. Okay? By properties of absolute value, you can break this into two absolute value notations, P minus Q. Okay, we know that the absolute value of 1 is just equal to 1, or we can just simply not write that. The remaining item here is the absolute value of P minus Q, which is the distance. Let me have the space here again. So we're moving here. This one. This is just equal to the distance between Q and P. Because distance between P and Q is Q minus P. Therefore, the distance between Q and P is P minus Q. So we have shown, again, this property to be true. Hence, again, whichever point is written first, we have the same distance. Okay. Take note, we are using here the absolute value property, or property of absolute value, which will also be used for proving a third one. This is very common. This is called triangle inequality, which tells us that if we have the distance between P and R, if Q is between them, the distance between P and Q plus the distance between Q and R is greater than or equal to the distance between P and R. This is triangle inequality. Let's try to show the proof of this here. P and R. Take note, that's actually R minus P. Now, what if I'm going to introduce the 0 here inside plus 0 minus P? So I could introduce here inverses. Let me have here R, let's say minus Q plus Q minus P. Because when adding these two, it's just equal to 0, so we're just going to return at R minus P. Okay. I'm doing that because there is a property, absolute value notations, where if we have here the absolute value of A plus B, this is less than or equal to the absolute value of A plus the absolute value of B. This is commonly known as one of the properties of absolute value. Hence, since we have addition here, we can actually look at like this, grouping R minus Q plus Q minus P, and then we can invoke this. As this is our A and this is our B, this is less than or equal to the absolute value of R minus Q plus the absolute value of Q minus P. Okay? They have this absolute value of A plus B is less than or equal to the sum of the absolute value of A and B. And what is this, by the way? This is actually, let me put equality here. This is actually, yes, equality of this expression, okay? But this is still less greater than or equal. This is distance between Q and R plus the distance between, interchange them, you have P and Q. So we have here the distance between P and R is less than or equal using this, not this one, okay? The distance between Q and R plus the distance between P and Q. Since our goal is this, of course, this is addition, you can always interchange that. Finally, the distance between P and R is less than or equal to the distance between P and Q plus the distance between Q and R. So we have shown the triangle inequality. So once this is actually important, because if you have situations where you have a problem in solving for a distance between vectors, you can use or invoke this to make it easier as you move forward. These are the three properties for the distance between points. Actually, there are four. The first one, which I did not include here, is that the distance is always greater than or equal to 0. We know that already. Distance is always greater than or equal to 0. Hence, I did not include that here already. Thank you very much for watching.